Robotic pushing is one of the simplest and most intuitive skills with a minimal robot end effector that can manipulate hard to grasp. An accurate pushing control strategy is required to achieve the robotic pushing tasks, but the hybridness and under-actuated nature of the pushing system and uncertain object properties make it challenging. In this paper, we proposed a goal-driven robotic pushing framework that can operate under uncertain object properties and without any predefined pushing trajectories. Based on our prior work that suggested the online model estimation to handle the uncertain object properties in practice, we employed the model predictive path integral as a goal-driven controller with modified version of the generalized force motion model. The modified generalized force motion model is an extended version of the generalized force motion model in that the robot's motion is extended from a single integrator into a double integrator. Through this modification, we can achieve more smooth robot motion and state-dependent input constraints formulation that makes the input clamping process becomes more tractable. Also, we employed the model predictive path integral as a goal-driven controller with the following cost function and input clamping processes. To show the feasibility of the proposed goal-driven robotic pushing framework, we first performed comprehensive numerical experiments in two scenarios, known parameters and unknown parameters. The three distinct pushing tasks were performed with three different object shapes, and we reported the total trajectory length, task success rate, and total simulation step as a performance index. To demonstrate that the proposed method can operate under uncertain object properties, we compared the proposed which combined MPPI and UKF-based model estimation process against the MPPI without model estimation as a baseline. The results of the numerical experiment in Figure 4 are as follows. As shown in these videos, the MPPI-based goal-driven pushing controller can push the object toward the goal state in known parameter scenarios. However, the proposed show more stable and reliable pushing motion than baseline in unknown parameter scenarios. Through the numerical experiments, we verified that the proposed and baseline did not show significant differences in known parameter scenarios while the proposed outperformed in unknown parameter scenarios. It implies that the proposed MPPI-based pushing controller can work as a goal-driven controller well, and the UKF-based online model estimation process is necessary to overcome the uncertain object properties. Also, we computed the offline generated optimal pushing trajectory using full-time prediction horizon MPC. Although it can generate more length optimal trajectories, it is an offline process and only valid if the model parameters are exacted. To demonstrate the proposed goal-driven robotic pushing framework can work in real world, we also performed real robot demonstration with two pushing tasks under unknown parameter scenarios. As shown in these videos, the proposed also worked well in real world, and we can observe the MPPI with a long-term prediction horizon can mimic the phase switching mode. In conclusion, the contributions of our work are as follows.